In this video, we'll dive into Faraday's law, and we'll begin by analyzing it in the simplest possible context. So Faraday's law tells us that the EMF in a loop is equal to negative the derivative of the magnetic flux through that loop. Let's see what it actually looks like. We're going to consider a region in space which has a radius of r. And in that region of space, we've got a magnetic field which is linearly increasing in time. So B of t is equal to B naught t. Let's break down the steps. As a first step, I'm going to consider what the magnetic flux in this region looks like. Remember that the definition of magnetic flux is that it is equal to integral B dot dA. And so we'll take this step by step. As a first step, I'm going to consider the dot product. B and dA are parallel, as you may remember this from Gauss's law. dA is the normal vector to the surface, or its direction is normal to the surface. And so we just get magnitude of B, magnitude of dA, cosine 0 is just 1. Next, I ask, does B vary across my surface? No, we've been told that it is uniform. It is dependent on time, but time does not depend on where in the loop I am. Therefore, we can pull out our magnetic field and be left with B naught t times integral dA, where I've plugged in our actual value for the magnetic field. And then lastly, integral dA is just the area of our loop, which in this case will be pi r squared B naught t. And so now we're interested in understanding what the derivative of this, in this case, that's fairly simple. d phi b by dt is constant and is simply pi r squared B naught. And so now the question becomes, what is the meaning of the negative sign on our EMF? The easiest way to understand this from a computational perspective is simply to think about the direction in which our magnetic flux is going, or rather, in which our magnetic flux is increasing. Our magnetic flux is out of the page in this case, and its magnitude is increasing. Therefore, I expect the direction of my EMF to be into the page. And what does that mean practically? Remember right-hand rule. Take your thumb and point it into the page, and what you'll notice is that your fingers wrap clockwise. And so, in essence, what we can view this as is as though we had a battery in our loop, which would be driving current in a clockwise direction, or driving conventional current in a clockwise direction. Why is that the correct direction? That's where we want to discuss Lenz's law. What Faraday's law tells us is that a changing magnetic flux produces an EMF, which can then, for example, drive current. And so suppose that our current, or our EMF, went in the counterclockwise direction. So let's assume that for a moment. What would that do? So if I have a current which is going counterclockwise, use right-hand rule, and you'll notice that it produces a magnetic field which is out of the page in the interior of our loop. And so what would the effect of that be? We have an increasing magnetic field initially within our loop, initially established. If that induces a magnetic field which is also coming out of the page, that's going to lead to a runaway effect where our rate of d phi by dt is forever increasing. And so Lenz's law can, in a sense, be seen as an energy conserving law. The effects of changing magnetic field are to produce a EMF or a current, which produces a magnetic field which opposes those changes, leading to an overall stabilizing effect. In the next video, we'll expand on this concept to consider all the ways in which magnetic flux can change, other than just being a function of time.